Okay. Welcome everyone. Today we're going to focus on sanitization. And sanitization is, on one hand, what slows the fuzzer down, but also what gives you an oracle to detect different kind of issues during the fuzzing process. Like as we learned in the fuzzing lecture, and partially also in the symbolic execution lecture, is that we need some form of oracle to detect if we have been hitting a bug, right? If we have discovered a bug. A fuzzer is good at discovering different kind of areas in the code and evaluating different kind of areas in the code. But the fuzzer needs an additional kind of input to say, hey, you've now hit a bug. You've now hit the bug, and you can now store this input on the side to actually detect or tell the developer to look into it for further analysis. So today we will focus on sanitizers and sanitization and try to figure out what good policies are and what a good trade-off there is between sanitization and costly oracles that we run on the side and very, very fast fuzzing. You remember on the fuzzing lecture and also in the software testing lecture that in fuzzing it's all about speed, right? We're trying to get as many executions through as possible. And fuzzing is an inherently is a technique that's inherently rooted in systems. So we are about optimization. We are about using the few cycles or the finite amount of cycles that we have in the best possible way to find as many bugs as possible. So fuzzing is an optimization game. We are trying to maximize the amount of discovered bugs. So this requires tuning, this requires heuristics, this requires adjustment. Now, intuitively, saying that we slow down fuzzing by halving the throughput, instead of 1,000 executions per second to 500 executions per second, sounds like a bad idea. But if we make it much more likely to detect a bug, then we actually can get a benefit out of it. With fewer executions, we can actually trigger more interesting behavior. Now, why is that, right? So without sanitization, if you write 1 byte past the end of the buffer, or if your program reads 1 byte past the end of the buffer, very likely nothing will happen, right? Because you're writing into some kind of weird, odd area, and it's very unlikely that the program will crash. Now, with a fixed policy enforced, as soon as you write 1 byte past the end of the buffer, the oracle can detect and tell you, hey, you violated memory safety. Now this is an actual bug in the program, and you need to go look at it and evaluate it, right? So you only need one input that writes past the end of the buffer. Without sanitization, you need inputs that write so far beyond the buffer that you either corrupt other adjacent data, or you hit a page that is not mapped and you get a segmentation fault. Right? So this is a slightly different policy that we are facing here. So the input needs to be very specific to actually trigger a crash. And in the state space, there's a lot of inputs that will not be able to trigger that crash. So this is why we're talking about sanitizers today. So we are planting an ideal set of bombs that go off whenever we violate the underlying policy that the sanitizer is enforcing. And we'll talk about different kind of sanitizers in the second part of the class. So a sanitizer is an instrumentation pass in the compiler that instruments the underlying program to check for different kind of violations according to the oracle that it enforces. Whenever the policy is violated, it crashes immediately. So the sanitizer will trigger, like will print out the report about the bug on the screen, and then trigger a crash of the program. This gives the fuzzer the signal that, hey, something bad has happened. And it will not exit 0, but it will exit with an actual fault, signaling that something has gone wrong. The fuzzer then triggers the fault and records these crashes, but not every fault crashes. Now with sanitizers, as I described just earlier, we can enforce the given security policy to crash the program right away upon violation, right, whenever that happens. So sanitizers make faults detectable according to the policy that they are enforcing. Now, this very much depends on the policy, and we'll discuss later about the different sanitizers. Not every sanitizer is worth it, right, because sanitization comes at a cost. Each additional sanitizer that you're adding slows down execution speed by half. So you get 2x to 4x overhead. If you would enable all sanitizers, this would be an incredibly high overhead and would usually not be worth it. So we need to figure out a policy or a point, how much sanitization is actually worth it to recover the cost of sanitization by the amount of bugs that we are discovering. And this is Crash Bandicoot if you've never played it. So the sanitizer analyzes the program during compilation, right? By now you should have all used some form of sanitizer, or at least played with sanitizer. I assume you have all played with ASAN, address sanitizer. Yes? No? So these are all yes? Cool. To learn different kind of properties during compilation. What does ASAN do? ASAN detects all pointer dereferences and then looks at where different kind of pointer dereferences are. Other sanitizers look for different properties, such as creating a type graph of the different type lattices that are used in C++ or other programs. They may look at different kind of threads, like locks or locking primitives, different kind of data structures that are being used, or so on, right? For inter-thread interleavings, race conditions, and so on. In the second pass, or in the second part of the sanitization pass, the program is instrumented. Right? So sanitizers are inherently a set of runtime checks. So after analyzing the program, the sanitizers figures out where in your program you are carrying out dangerous accesses, right? And then it instruments these dangerous accesses to make sure that there's an actual check involved. In addition to the checks that are being inserted, the sanitizer also inserts additional code to record information about the, for example, live objects. So for address sanitizer, it would record where in memory the different objects are, what the size of the objects are, and so on. For race detector, it would record which thread has last read or written a certain variable, what locks are being held, and so on. For a type sanitizer, the sanitizer would record what type a given object is to make it detectable when it is used as a different type, right? So the program is instrumented, recording metadata for the checks, and then to actually execute the policy checks on top of it. Now, at runtime, the code then executes all this extra instrumentation. Extra instrumentation being the recording of the metadata and executing all these additional checks. Right? So we are inserting quite a bit of additional code, and we are also executing quite a bit of additional code. This is just a regular compiler pass, right? Our compiler is already doing a lot of these kind of passes. And you likely know all the different optimization passes, dead code removal, code moving, loop unrolling, a whole bunch of other passes. And these are usually geared towards optimization. In security, we've talked a lot about mitigations, right? So mitigations like data execution, well, not so much, stack canaries or control flow integrity, they are also compiler passes, right? So stack integrity and control flow integrity are similarly compiler passes that enforce a given policy. So stack canaries, they record additional metadata, right? They insert an additional variable on the stack and actually read and write to that variable to execute the checks whenever you enter or you exit a function. So stack canaries could be considered a form of a sanitizer. Now, where's the difference between a sanitizer and a mitigation? It's kind of difficult to differentiate between the two because the line is a bit blurry, especially for stack canaries and control flow integrity, because both of them require additional metadata, record additional metadata, and execute additional checks. Now, for a mitigation, the intention or the goal is to stop exploitation. It's not to record and report additional information, whereas for a sanitizer, you're trying to record sufficient amount of information to tell the developer what has actually gone wrong, right? So the goal of a sanitizer is that if you use address sanitizer, it tells you, hey, this variable over here, you allocated it over there in the program and then used it over here, and this is where you wrote 2 bytes past the end of the buffer, right? So in an attacker context, this report would not, like writing this report to the console would not be a good idea. So part of this, the reason for this is the report acts on corrupted data. Well, let me try to refine this a bit. As soon as you detect, for a mitigation, as soon as you detect that the policy was violated, the only safe option you can do is terminate the program immediately. Why is that? Yeah? Why? Right, right. So for a mitigation, you have to assume that the attacker has changed all memory. Right? So for a mitigation, you assume that the attacker that has corrupted or triggered a memory corruption has completely changed all memory. So as a mitigation, you can no longer assume that reading any kind of your data is still your data, because the attacker may have modified this in arbitrary ways. So the only safe action for a mitigation is to terminate immediately and trigger a fault, and then actually exit the program. Now for sanitization, you are running this in a different context. The perspective is different. You are running this in a debug context or in a developer environment, right? You're trying to detect what has gone wrong and how it has gone wrong. So it's perfectly okay to collect additional information as you're triggering a bug. You're not running in an adversarial context. You're not assuming that the attacker has already completely modified all of your memory. So you can collect information and try to report it. Now, for address sanitizer, this information may be wrong because you've completely corrupted and overwritten half of your stack. This can happen, right? But this is still a debug environment, and you're not acting on adversarial data. You had a question. Yeah. So the question was if a programmer inserts checks to verify different kind of input data, if this is a sanitizer as well, or if this is part of the program. Now this is part of the program. We call this sanitization too, so the word is overloaded. So when you as the programmer, you carry out specific checks whenever data is being sent to the program, this is called input sanitization. Now unfortunately, like we use the word sanitization in the context of sanitizers as a debugging tool or as a developer tool, and as the sections of code that have been inserted to check input data. This is a bit unfortunate that we're not using a different word, but it's two different concepts, and you have to specify which concept you're looking at. What do you mean? Policy violation. Hmm. So is the question that like for the input sanitization checks that you're adding, if the that could be, for example, this is a prime number and the prime number detector is wrong, that the user program would not answer correctly if this is a fault or not, or right? So if you're asking for faulty or partial checks of the programmer that are not right. So if the programmer did not implement all checks correctly and then you trigger some other behavior with wrong data. Not necessarily a memory fault, but you would consider 8 to be a prime number in your example. I think I'm not getting you. Can you try to rephrase? Mm-hmm. No, this is regular program behavior. So if you as a programmer, you have additional checks that make sure that the program conforms to a specified behavior and you reject illegal input, this is fine. This is just expected program behavior. Now I thought or I wondered that you were aiming at the programmer not implementing all checks correctly so that, for example, the programmer has a input prime number please and then the prime number check is not correct and it would accept 8 as an example as a prime number. Right? So this would be a fault for a policy that this needs to be a prime number. Now we can discuss how we can create a sanitizer for that because these are logic bugs. There's no sanitizers that exist for these kind of bugs so far because this would require an actual program specification. So if you had a perfect formal specification of how data should look like at each part of the program and how control flow should react between different parts of the program, you could enforce these checks and you could synthesize these kind of high-level checks based on this formal specification to then detect logic bugs. Unfortunately, programs neither have formal specification nor is it really feasible to synthesize these kind of logic bugs. Today we'll talk about much more baseline policies such as memory safety, type safety, some undefined behavior that is being triggered as part of the language and language violation and for example race conditions. So these are policies that can actually be checked by a compiler easily, right? It took 40, 50 years of C to actually get to this, so the easily is in quotes, but it is checkable, and we can come up with checkers. Now, what you brought up or touched a bit is an interesting angle here that we need to come up with kind of high-level policies. So if you look at Python programs, PHP programs, Java programs, right? So the question is different. We are not interested in these, well, except for race conditions, we are not really interested much in these kind of sanitizers. They would not be useful. But we would like to enforce some kind of high-level policies to detect logic bugs, which will be the next big class. So if I envision where the development of sanitizers in 5 to 10 years will go to, this is exactly the area of logic bugs, and I think this is a really, really interesting area to look into. How can we define efficient, tight policies based on logic behavior of the program, and then how can we make this checkable based on a sanitizer? Yes, please. Now, this is an interesting question. Do you? right? This is an unsolved research area. So yes, you could ask the developer to write the specification. That's one possibility, but there could also be other possibilities. What I have in mind, imagine we have perfect compartmentalization. We break large and complex programs into smaller pieces. Then we can actually look at the interaction between these compartments. Like from compartment A to compartment B, there's like an API. And now we can actually write the specification for the API. What is correct usage of the API? And at that level, we could detect different kind of violations. So this may be it may not be perfect, but none of the sanitizers are. Right? So this would be a step towards making it more tangible. And because programmers are never going to write the full specification for all of the program. This is just not possible for any reasonably complex program. But it may be possible to look at certain APIs and then write the specifications for the interactions for these APIs. But yeah, interesting question. And we'll see in 10 years. Maybe we'll have a beer in 10 years and discuss what happens when you folks come back. So good. We already talked a little bit about what different kind of policies are interesting, what metadata is needed, and so on. And we'll now go a bit into how sanitizers work in more detail. And we'll start with address sanitizer. You've already worked with address sanitizer. You already know address sanitizer a bit and what it does. And address sanitizer it's actually the first sanitizer that came up. It instruments every single memory access. So each memory read and memory write, based on a pointer, checks if the read or the write is correct. So is it even if it's a 1-byte read or an 8-byte read, all the reads and writes are being checked. The advantage is that the checks are really, really fast. Right? So address sanitizer was designed so that the checks would be extremely fast and extremely efficient. Now, the disadvantages are, well, the memory overhead is 1.5 to 3x. So this is quite hefty, right? This is quite a bit of additional memory overhead. If you're trying to analyze Chrome, that already requires 16 gigabytes of RAM, you suddenly require like 40, 50 gigabytes of RAM to run Chrome in sanitizer mode. It's still slow, so it's about a 2x slowdown on the average case, and it is not a mitigation. Now let me tell you a bit why it is not a mitigation after we go through the policy that it actually does. So whenever you allocate a buffer, and this is the figure here on the right hand side, you allocate a buffer of 4 bytes. You can access the buffer, you get a pointer to the buffer. Address sanitizer pads this buffer with 2 red zones. Right? So every time you allocate such a buffer, the address sanitizer instrumentation will allocate 2 more buffers before and after your buffer, and then fill it with magic data. If any of the reads or the writes of the program then end up reading or writing one of these red zones, address sanitizer detects a fault. And we will talk about the implementation of the red zones in a bit. Now, this is great, right? So this allows us to detect whenever we go past the end of a buffer. Now, what kind of memory safety violations does address sanitizer not detect? You have a question? You mean for stacked canaries? You mean for stacked canaries? So the question was for the recording, what is the relationship between stacked canaries and address sanitizers? So stacked canaries, they only target, like the canary would be only 8 bytes. For address sanitizer, the canaries are larger, like the red zones are larger, but the implementation is very, very similar, right? The key differences are for stacked canaries, you only check when you return from the function. Here you check for every read or write. And for stacked canaries, you only have one single such canary. So the goal is to have this this much simpler with much lower memory and performance overhead. Stack canaries cost about 2%, 1 to 2% performance. Address sanitizer costs 100% performance. Yeah? Um, sure, but stacked canaries are strictly weaker than address sanitizer. So if you compile with address sanitizer, you would have many more checks, and you would simply remove the stacked canary instrumentation because you don't need that mitigation. Right? So stacked canaries, you can think of stacked canaries like a small red zone for that is just once per function, checked once per function. Right? So it's much simpler and a strict subset of the checks that address sanitizer does. Given that it's a strict subset, you can also remove it because you would just do this one additional check, if that makes sense. Cool. So what kind of bugs can we not detect with address sanitizer memory safety bugs? Yep. What do you mean with an arbitrary write? Okay, let me try to tease this apart. You're saying that you can detect continuous writes, but you cannot detect arbitrary writes. You cannot detect the subset of arbitrary writes that do not hit a red zone. So this would be the precise answer. You can detect arbitrary writes that hit a red zone, but you cannot detect arbitrary writes that go, for example, to the next buffer that is adjacent to like above the other red zone there, right? Correct. So address sanitizer cannot detect arbitrary modification to the pointer that would go beyond the next object or the next red zone. Yeah? Correct. So address sanitizer checks whenever you dereference a pointer that you're not targeting one of the red zones. An alternate, like we talked about softbound, right? As part of the memory safety class. And softbound checks the pointer. So softbound detects whenever you modify the pointer. So softbound actually detects, is it still recording? I think so, yeah. So softbound actually detects when you modify the pointer. So softbound does not need red zones because softbound detects, hey, this is the object and I've now modified the pointer past the end of the object. And when I'm accessing this pointer, I can actually trigger a fault without adding this red zone. But it comes with a massive amount of compatibility issues. So you could not use softbound on Chrome because the software is simply too complex. Hell, you cannot even use softbound on all the spec benchmarks because of different kinds of compatibility issues. But red zones and address sanitizers are highly compatible because the only thing you change is you pad the allocation left and right a bit, or before and after a bit, and you instrument every single read or write. Right? So this is much simpler. But it comes at a trade-off that you cannot detect arbitrary writes that go beyond the end that actually hit another buffers because you have no information about the pointer itself. Right? So you don't know what the pointer itself does and you have no information about that pointer. You only know where it is being read or written. So intuitively, the larger the red zone, the more likely you will detect a bug. But the larger the red zone, the more additional memory you're actually using. So there's again this trade-off that we are facing here, right? So address sanitizer is highly compatible with current code. Works for pretty much everything, has only a 2x slowdown, but the memory overhead is kind of massive, and we have to trade off additional memory overhead and the detection capabilities. So 32 bytes turned out to be a very reasonable padding, because most bugs only go close to the buffer itself. Okay, are there other kind of bugs that we cannot detect? Let me ask, what other bugs we cannot detect? Yeah? Yes. Reads and writes. What else? Well, let's stay with memory safety. But we don't have type checks. We cannot detect logic bugs either. These are outside of scope of what address sanitizer does. Address sanitizer targets memory safety, but there's another kind of memory safety bug we cannot detect. Yeah? We can detect use after free. So whenever, but probabilistically, we'll get there in a second. So for use after free, whenever an object is being freed, we'll just recolor whatever buffer occupied with red. And then as long as this memory is not reused, we will detect use after free. And then the goal is to delay the reusage of memory for as long as possible, and then it becomes a probabilistic detection for use after free. Similar to that, it's a probabilistic detection for arbitrary writes that jump outside of the buffer. Yeah?
I was wondering how it works. Like, is it like replacing the call to malloc, scanloc?
Yes, we're getting to the implementation in a bit. What other bugs can we not detect? What instead of allocating a buffer, we are allocating a struct? Yes, intra-struct overflows, right? So inside a struct, if you have multiple fields, if you're overflowing from one field to the next, we cannot detect that, because the red zones will only be placed before and after the struct. Now, we could change the layout of the struct, but this would break compatibility with code that is not instrumented, right? So we could change the struct itself and add additional red zones into the struct itself, but this would completely break compatibility with any of the code that is not instrumented. So address sanitizer does not instrument structs themselves and doesn't add red zones between elements of a struct. Right? So similar to that, arrays, right? If you have an array of structs, or an array of buffers, if you go from one buffer to the next, you cannot detect that with address sanitizer, because the red zones will only be placed at the beginning or at the end of the buffer. Or even more so, if your application uses an allocation pool, right? You're allocating 40 megabytes of memory, and then your application does the allocation inside that memory pool. Like, this is surprisingly common in software. I don't know who came up with the idea of doing that, but somebody thought in the 90s that this was a clever idea, and most code that's fairly old actually uses that. They just allocate a large chunk of memory and then use the allocation inside that memory. So if you don't, and address sanitizer will happily place a red zone at the beginning of your 40 megabyte buffer and at the end of your 40 megabyte buffer, and then it will not detect anything inside. Right? So intra-object overflows are not detected. These are all the same class. Anything else that comes to mind? I don't know anymore myself. So if you do know, let me know. But these are the two main classes. So not hitting the red zone through arbitrary pointer modifications and intra-object overflows. They are just not visible for ASAN. Now, in just 3 years, Address Sanitizer found around 7,000 bugs, and it keeps finding bugs again and again and again. So this is extremely effective as a policy. Address Sanitizer finds memory address bugs. It focuses on buffer overflows, like on the heap, on the stack, and for globals, and has very limited support for use after free that is probabilistic. So it detects some of the spatial and some of the temporal memory safety violations, but cannot detect all of them. The sum is large enough in practice that it's going to be extremely efficient. Especially if you're using it with fuzzing, it's highly likely that one of the violations will, one of the iterations will actually trigger a violation. You have a question? It is being reused, right? For the use after free. Like at one point in time, the memory allocator will say, oh, we'll just reuse this memory. And then it will again be uncolored. Right? So this is why, like, you don't apparently most machines don't have infinite amounts of memory. So at one point in time, you'll have to reuse the memory, right? And then you're recoloring it from red to white or whatever other color you're using, right? So you're just decoloring it. Cool. Other questions? Yes. Yes. Right. Now this is an interesting question, and we can go into a heated debate about this. And it's a very interesting question. Why is this not a mitigation? Well, that is just one part. The other part is it's the cost is just too high. Like 3-4x memory overhead, 2x 2x performance overhead. That's just way too much. If you look at stack canaries, it's similar to stack canaries, but stack canaries comes at the cost of pretty much zero memory overhead and 1% performance overhead. So stack canaries are extremely cheap. Now, this is a weak argument. I know this is not a strong argument to differentiate between the two. The stronger argument would be that an attacker that has an arbitrary right, this is the attacker you protect against, can get past the sanitizer as a mitigation. So for any sufficient bugs that you will find, you will be able to use an intra-object overflow to corrupt a pointer to then go beyond it. So the cost-benefit trade-off is clearly not worth it. So this is why it is not being used as a sanitizer.
Basically, to determine if something is a mitigation, you consider the cost-benefit trade-off, and if it allows for perfect.
Right. So data execution prevention protects against arbitrary code injection. Therefore, it is a mitigation. ASLR shuffles memory and makes exploitation much harder. Therefore, it is a mitigation. It comes at zero cost. Right. Same for data execution prevention. ASLR. Now, ASLR is in this odd spot where it is a mitigation that is somewhat weak, but it came up in the late 90s, early 2000s, and it solved an immediate problem because all the exploits at that time were using stack-based buffer overflows to override the return instruction pointer. So it was a mitigation that was designed. So think of it as it is being grandfathered in. It's a legacy mitigation. Yeah. Well, and still, right, even if you have a stack-based buffer overflow now, stack canaries will make it much harder to exploit at pretty much negligible cost or very low cost. Does that make sense? Yeah. It's not perfect. I'm aware of this. That it's not a. Like in the end, a sanitizer would just have too high a cost.
I think the justification, but it's basically arbitrary.
Yes. Yes. Yeah. Right. Correct. It's an argument, right? Now, for like if you run address sanitizer, you could also run Java code and get rid of all the memory safety issues. but then you would have to rewrite it in Java. So that's another point. Yeah, you had another question? Right, but that's more a symptom, right? Mitigations are shipped to customers. Sanitization is not shipped to customer, right? But this is more a symptom that allows you to decide after the fact. The argument that you make as a developer to decide if something is a mitigation or not is somewhat more fine-grained. You have to consider the cost, right? Like tripling, quadrupling the memory overhead is usually a no-go, right? How would you say that? Like Chrome uses 4 gigabytes of memory on most machines. Just making the limit 16 gigabytes would be kind of a tough sell, right? And then just slowing down performance by half would also be a tough sell, right? So you would have a very tough time selling this as a mitigation. Now, as a soft-bound could be considered a mitigation for high secure context because it gives you a much stricter policy. Yeah. Right, so you could consider this that in a high secure context you would enforce something like soft bound to make sure that exploitation is not possible. But then it's an odd trade-off where you look at where do you draw the line, right? So address sanitizer could be a generalization of stack canaries, but then you would assume that an attack, like if you would be willing to pay the cost of 2x performance overhead, you would assume that the attacker could find an arbitrary right. Right? If your program is that buggy that you need to pay that. If you would apply soft-bound, which detects pointer modifications, you would, as the developer, you would accept to rewrite part of the software to make sure that it actually compiles with soft-bound to adhere to these high security standards. And you would be okay with paying 2-3x performance overhead, and then you could consider it as a mitigation. But for regular user computers, mitigations are a couple of percent, like 1, 2, 3%. CFI has like 0.5, 1% overhead. Stack Canaries has 1% overhead. ASLR has 3 to 5% overhead. Right? So these are all in a very, very limited performance budget. Make sense? Cool. So let's talk a bit about the implementation. The implementation of address sanitizer is due to through a compiler module, which is in Clang and GCC. At compile time, it instruments all the loads and stores that are then, the instrumentation is then executed at runtime. It pads stack global variables as red zones, and the runtime module intercepts all calls to malloc to then pad the allocated object. And it does some additional bookkeeping to keep track of what has been allocated. We'll do a quick example. You've already played with address sanitizer, so this will not be too new. So this is a simple example, the same as I have on the slide. The code, we do have a global object, we've got a stack object, we've got a pointer. Both the global array and the stack array are 16 bytes long. Depending on the first argument, the value of the first argument, we either make pointer point to stack, to a global, to malloc of 16 bytes, or a malloc of 17 bytes that is then being freed. So this is stack-based buffer overflow, global buffer overflow, heap-based buffer overflow, and a use after free. And then we trigger an illegal read. We can use address sanitizer by simply calling Clang. We're going to do some optimization, so O1, and then fsanitize equals address, and then just add the file. If we don't add sanitization, you see nothing happens, right? So this works just fine. All the calls actually completed. We were able to read and access 1 byte past the end of the buffer or illegal memory and so on, and no fault happened. So this, during fuzzing, this wouldn't trigger a fault. Now, if we would compile this with address sanitizer, and we run this again on the stack, we see that we have accessed a couple of bytes on the stack, and we see the address sanitizer tells, hey, there's a stack-based buffer overflow at this address, and this is in the demo file. In this file, let's add some debug information, so maybe we get some nicer information. Yeah, here we know it's in line 14 in that file. Super nice. It's been allocated here on this line. Okay, very nice. And here is the memory access to stack array, and we see the length of the buffer, right, where the legal access has actually happened. Did I say 16 bytes? I think it was 16 ints, right? Yeah, so it's 16 ints, not 16 bytes. I misspoke. So it's 64 bytes long. Okay. If we run on the heap, we get a very nice report as well. Global. This is a global buffer overflow. 0 bytes to the right of variable global. We get the same for the heap. Right, so this is super handy. And we always get this nice report where the access is and what has actually happened. And same for the heap use after free. Yes, question?
What does -f no common do?
The no common libraries, I think. Good question. Flag specifies that variables without initializers get common linkage. Yeah. I think it has something to, like, I added it because of the AZN library. Good question. ManPage helps you. But yeah, thanks for asking the question. Now everybody knows. Good? Okay. So, what metadata would we record there? What kind of operations would we instrument? What kind of optimizations can we think of? How would you detect out-of-bound accesses? And how would you detect use after free accesses? We've already talked quite a bit about metadata operations and so on. I would like to know how you would implement the red zones and how you would detect these out-of-bound accesses and use after freeze. So how would you implement these kind of checks? Any ideas? You've already answered a bunch. I hope for somebody else. How would he implement this? We now know conceptually that we want this red zone, right? How would he actually do that? Yeah? Okay. That's a very good idea. This is what how it's conceptually done. You save in some form of data structure the range of that red zone or of the red zones, and then check at runtime if it is in that red zone. What kind of data structure would you use to store these red zones? Now it has to scale to the number of allocated objects on the heap and on the stack and on all globals, right? This can be quite high. What kind of data structure would be a good fit? Yeah? an interval search tree, a red-black tree maybe. Yeah, that would be an option. We'll get back to that in the second part of the course. What else? What is more efficient? Like this gives us log n access, right? I want O1. Otherwise, the overhead is going to be too high, especially for large numbers of objects. Like log n is going to be too costly. Yeah, a hash tree. This gives us O1 complexity, but it's still too costly. Sorry. it gives us OC for constant, but the constant is too high. I want O1. Yeah? Yes, perfect. Yes, we'll use a bitmap. This gives us O1. Perfect. And this is exactly what is being done. And then we just check in this bitmap if it is being used or not. The simplest form would be we halve the address space and we just add an offset to that address space, right? This could be a simple implementation of the bitmap. Let's see what we do. So data structures for metadata is, as some of you mentioned, right? We can have a two-level. No, nobody mentioned that. We could have a two-level lookup structure. Stay. We could have a red-black tree. I think this was mentioned with the interval trees. We could have a bitmap. This is the flat compressed map, right? We could have a 1 byte for each 8 bytes. So this trades space for speed, a two-level lookup table similar to a page table, and then you do a software implemented page table lookup. This would trade some of the space into speed. This would be O2 access, but would reduce the cost of the memory that we have. Or a red-black tree, which would be very, very compact, but would be fairly costly to access, where we hit log n. So we get O1, O2, and log n access overhead. What ASN actually does is it allocates like a 20 terabyte memory area, 4 terabytes for the heap, and then 16 terabytes of shadow memory in a 256 terabyte address space. How is this even possible, right? Well, luckily this is virtual memory, and as you may remember from your operating system class, virtual memory on all systems, it's just given out to programs. It's not really allocated on the back. Now, the data structures used for these 16 terabytes of memory still use a couple of megabytes to hundreds of megabytes of memory. But you're only paying for those subsets of memory that are actually being allocated. All else is zeros, right? So make sure to never initialize this data structure with ones, because then you have to pay the full 16 terabytes. But as long as you are not accessing that data, it will just be zero and not be allocated, right? So this will just be fine. So this is how Address Sanitizer actually does the allocation. 16 terabytes of memory. This is crazy, right? It's a large amount of memory. Even for modern computers, 16 terabyte is a lot of memory, right? So out of the 256 terabyte address space, we are allocating a subset of 16 terabyte for the shadow memory and to make sure that we can actually access there. And then we let virtual memory or the virtual memory subsystem handle it to make sure that this actually works out in practice. What do we store? You mentioned a bitmap. Like we could check individual bits. Now accessing the metadata is O1, but checking individual bits is again OC, which is too high. I want again an O1 check. So we're not going to store individual bits, but we're going to do an encoding that's a little bit more clever than that, right? So for each word in memory, we are going to, like for each word, for each 8 bytes, we are allocating 1 byte of metadata. Fair enough, right? So this would give us 8 bits, and we could store individual bits. This would give us the opportunity to say that this byte is allocated, this byte is not allocated, this byte is allocated, this byte is not allocated, and so on. So this will give us a very fine-grained access, but we don't need that, right? For any 8 bytes, it's either most of the time all of it is allocated or nothing is allocated, right? Okay. If part of it is allocated, it's a part from the beginning towards the end. Because if you allocate an 18-byte buffer, we have 2 blocks of 8 and then 1 block of 2 with 6 bytes empty that are not going to be used by the allocator due to padding. So what we store in this byte is simply the amount of bytes that are being allocated. So if 1 byte is allocated, we store 1. If 2 bytes are allocated, we store 2. If 6 bytes are allocated, we store 6. If 8 bytes are allocated, we of course store 0. By 0, you'll see in a second, because again, this allows another optimization to speed up the checks. But if it's if a subset or a part is allocated, we just store the amount of bytes that are being allocated. So encoding assumes that only the first k bytes are accessible. The shadow entry stores the number k for each word. Larger words translate to smaller metadata. So we could also have blocks of 32 bytes per byte, 64 bytes per byte. But the trade-off is that we lose a lot of memory due to additional padding. The metadata access, the one axis I was talking about, then becomes the simple axis. We take the address, we shift by 3, and we add the base address of the shadow table. This is it. It's amazing, right? So we add the base, we take the base address where our shadow table is, we shift the target address that was used to access by 3, and then just add those together and access it. So this is a one single instruction. And we get our byte. Now we have to figure out the instrumentation for the check. This is a get data if you get a long address, so if you get 8 bytes. We do the shift that we've just seen, so we shift address by 3, add the shadow base, and then the null check makes this easy. If dereference shadow, if you read that byte, then we report an error, right, if it is 0. This is a very simple check. So this is 2 instructions for accessing the metadata, loading it, and then doing a check. So we can implement this memory safety check in 2 instructions for every single read and write. And this is really, really fast if it's an 8-byte access. If it's a partial access, so for example, if you're reading an integer, as in 4 bytes, we again, with one instruction, O1, we calculate the location in our metadata table. And then we check shadow plus, we have to do this additional calculation here. Right, address and 7, so we just get the 3 bits, plus 4 minus 1, so we check if the right amount of bytes is accessible, if all the bytes in that area are accessible. Right, so this costs us 2 more instructions for partial accesses, but most of the time we just access the full word. Okay. And we can generalize this to an arbitrary n axis from n being 1 to 7 in address and 7 plus n minus 1 to do this actual check. Right? So this is very, very clever and highly optimized. So this is how you see how the internal plumbing here actually works. So let's talk about the implementations or the instrumentations for a bit. What do we do on the stack? On the stack, the address sanitizer instrumentation adds the red zones around the objects on the stack and poisons them whenever we enter the stack. When the function exits, we depoison them. Right? So if you have this function char with an 8-byte array and then user code, address sanitizer would add a red zone before the object and 2 red zones after the object. First, we would pad to 32 bytes, and then we would add another full 32-byte padding. So first padding to 32 bytes and then a full padding afterwards. You see the calculation of the shadow address, and then we would insert static instrumentation to just taint these bytes. So we would poison the full red zones there, and then we would have a 8-byte value, the 00, that is actually accessible. And at the end, before returning from the function, we would depoison the shadow values again and make it accessible again. Right? So this is how the instrumentation works on the stack. For globals, the address sanitizer instrumentation would simply add a red zone after the original value. So we turn it into like add a 60-byte red zone, so it's first again pad it to 32 bytes, and then add a 32-byte byte red zone, which again would make it 32 byte aligned. Why is there no red zone before the original value? Yeah? Right. There's already like if it's the first one, if it's the first global, we will get a segmentation fault if you go before, right? Because there's no page allocated. Otherwise, if it's the second, you just have the red zone of the first one right ahead of you. Good. The runtime library initializes the shadow map, at least the base structures at startup, and then malloc and freeze update the metadata as well and pad the object with the corresponding red zones. In addition, the runtime library intercepts special functions such as memset and string copy and so on to make sure that we can actually detect those. So as a summary for address sanitizer, we've learned how address sanitizer detects all the different kinds of memory errors. It places red zones around objects and checks those objects on any kind of trigger event, such as reads and writes. And the tool can detect all the different kinds of bugs as follows: out of bounds, use after free, use after return, use after scope, double free, invalid free, and so on. The cost of address sanitizer is about 2x, same as the memory cost. And the beauty of it, it's extremely simple. Clang as sanitize equals address, your target, and you're done. Questions for address sanitizer? If not, you can also ask the questions during the break. I would suggest you take a 10-minute break and come back at 20 to 12. So a lot of the questions actually focused on differences between softbound and address sanitizer. So address sanitizer does not store anything about the pointer itself. So it's very, very lightweight. Well, conceptually lightweight. Let's put it that way. So it's conceptually lightweight, and it simply pads space between these objects of interest. And then the instrumentation detects if any of these void areas are being accessed. Right? So conceptually, this is extremely simple and highly compatible with a lot of existing code. It has the issues of intra-object overflows or hitting other objects that it cannot detect. Softbound, on the other hand, keeps additional metadata on all objects and on the pointers themselves. This is conceptually much more heavyweight, but a complete implementation of memory safety for these languages. So this allows you to conceptually, softbound allows you to conceptually detect all memory safety violations. Why is softbound not used in practice? Well, it doesn't scale. It doesn't work for real code. There's way too many applications that just use a couple of bits in a pointer to store additional information. Right? For example, Blender, a common video encoding software, uses the last 3 bits to store what kind of type the object has. Right? And then just shifts and uses these bits freely whenever data is being accessed. other bits are being used for garbage collection in Python. So this makes it impossible to use something like softbound on real code without changing this underlying code. Now there's a debate if you should use these bits in a pointer, and the answer is you should not. But de facto, a lot of code does. Therefore, if you want your sanitizer to be compatible, you'll have to use something like address sanitizer. While softbound is much more pure from a conceptual standpoint, a simple approach, such as address sanitizer, actually works in practice. And you see that address sanitizer, softbound, it has a lot of citations. It's a great paper to read, but it pretty much stayed an academic exercise. Whereas address sanitizer is now being run on billions of machines or billions of cores. Right? So the impact of that in the bug finding capability is much higher because it actually fit a niche, how it can be used in practice without the developer having to change all the code. Other questions for address sanitizer? Crickets. Cool. We'll go on. There's other sanitizers around as well. There's memory sanitizer, not to be confused with memory sanitizer. I think each year I have like 5 students that confuse address sanitizer and memory sanitizer. Don't be that student. So memory sanitizer is just like detects uninitialized reads. How do you detect uninitialized reads? We assume the same instrumentation as address sanitizer, or the same metadata as address sanitizer. How do you detect uninitialized reads with this data structure? Yeah? Right, we use that, and what's the instrumentation? What does the instrumentation do? How do you set the bits? A green zone. When do you set the green zone? Correct, right? So whenever you allocate, let's stay with the red zone. Whenever you allocate an object, let's say we get rid of the red zones left and right. Whenever you allocate an object, you just color all the data of that object red. Whenever you write, you clear the red bit. Whenever you read, you check if that byte is accessible or not. And you've got an uninitialized sanitizer. Right? So when you allocate an object, you color it red. When you free the object, you color it white again. When you write, you mark that byte as written and accessible. When you read, you check if you're hitting a red zone or not. So is the question why address sanitizer does not do this in addition? Yes. Right, you would have to have 2 different kind of red zones. You would have to have a red zone that can turn into a green zone, and you would have to have a red zone that stays a red zone. Right, and then distinguishing between these 2 types of red zones would be not hard, but it would add extra instructions. Right, for each write, you would have to check, am I writing to a red zone inside the object, or am I writing to a red zone outside of the object? And therefore, to distinguish these 2 cases, and this would require a couple of additional ifs, and then it would have like 8x overhead. Make sense? For the others, right? So the question was, why does address sanitizer not check for uninitialized accesses as well? And the difficulty here is that for any write, the read stays the same, right? The read instrumentation is exactly the same. But for the write instrumentation, address sanitizer would have to distinguish between cases that you're writing inside an object and you're clearing the this has been initialized bit, or outside of the object. And this would make the implementation of the check so much more complicated that it's not worth it in practice. You had a question? No, they're exclusive. You take the input, you compile your program with the 4 different sanitizers, and then you run each sanitizer one after the other. We try to make them compatible. Some of them are somewhat compatible, but it's a hit or miss. It's also usually because the metadata is very different, right? You could add, for example, 2 different red zones, two metadata, one for the initialized data, one for the red zones. So it would require so much more additional overhead and a redesign, right? So each of the sanitizers are pretty much on their own. Slowdown of this memory sanitizer is up to 4x. Why is the slowdown so much higher compared to address sanitizer? Yeah? You are, well, partially correct. You are initializing much more data, right? For each object, like in address sanitizer, for each object you're writing 64 bytes, the 2 red zones left and right. Okay? Here you're initializing the object. The average object size is more than 64 bytes. Therefore, on average, for each object you're writing more memory. Okay? So that's one part. What other higher overhead is there? So one part is you're just writing more data. What else? Right, that's the same argument. You're writing more data, yes. Oh, you're meaning more writes? Yeah, because for each write, instead of just doing a read, you have to do a write, so this leads to higher memory traffic, worse cache behavior, cache synchronization among cores, and this adds to the slowdown. Yes. Cool. Those are the 2 main reasons I had in mind. Any other reasons that you can come up with? Good. Undefined behavior sanitizer, UBSAN. That's the second most commonly used sanitizer. It detects undefined behavior. It instruments code to trap on different kind of C language semantics and may detect underlined, unsigned, misaligned pointers, signed integer overflows, conversion between floating point types, illegal use of null pointers, weird pointer arithmetic, and so on. Right? The reason why this is a sanitizer and not done in general is that there's just too much bad code out there. So this would flag a lot of bugs in the code. Everything UBSAN actually flags should be fixed. One of the difficulties is that UBSAN flags a lot of current code. So if you don't have a modern project with modern style code, this would just flag way too many bugs for it to be fixed reasonably. The slowdown depends on the amount and frequency of the checks. It could be deployed in production, but it rarely is because of the additional the large amount of bugs that it finds. Now, these bugs may or may not be security critical. This is more like a software engineering tool, and they could be considered in part as code smell, as they highlight areas of the code that if the compiler gets more clever, this could turn into a bug. Right? Undefined behavior is what the compiler exploits for optimization to make programs faster. So the compiler leverages all the different areas of undefined behavior in the programming language and in the program to figure out ways to optimize this. For example, if you're writing to a memory area without reading from it again, the compiler will just remove these stores. Now, this has impact on security critical code. For example, imagine you are reading from std in from the terminal the password, and you're storing it somewhere in memory. You're computing something on a password, maybe a hash, and then you want to make sure that the password no longer is in memory. And you're just overwriting the password array with all zeros. Like you have an array from 0 to length of password array. You just overwrite it with all 0 characters. If the compiler can analyze and prove that there's no read access to that variable after the fact, after you have cleaned it, the compiler will simply remove these writes. Because from a language perspective, from the programming language perspective, the code executing with this cleaning, like with writing all zeros, is indistinguishable from code that executes it, or with or without, right? So the effects of the code are indistinguishable if the cleaning is there or if it is not there. Now, if your code has a bug, then all the bets are off, right? And the compiler assumes that your code is bug-free, because that's the underlying assumption of compilers. And all the optimizations are done under the optimization that your code, under the assumption that your code is bug-free. So this is one example of undefined behavior that leads to weird and odd bugs. Cool. Another one is thread sanitizer. So thread sanitizer finds data races between threads and focuses on like data races involving writes. So it keeps track for each memory write, and in the data structure it actually writes which thread ID wrote to a certain area last, and it also keeps track of locking primitives to make sure that what different data accesses, how different data accesses are shared. So for thread sanitizer, it allows you to detect write after write, read after write, and write after read data races. Slowdown is 4 to 10x with 5 to 8x overhead. So this is memory overhead. So this is quite hefty. But it allows you to figure out different kind of data races between threads, or if you're missing some synchronization or whatnot. Cool? So there's a fairly large family of sanitizers. Address sanitizer is the most common one. There's leak sanitizer that also detects memory leaks in addition to address sanitizer. Leak sanitizer is an extension. I think that's the only composable sanitizer. So leak sanitizer simply hooks into address sanitizer. Whenever you allocate an object, it just adds it to the list of allocated objects. And on exit, it checks if this list is empty. If the list is not empty, it will just report, these are all the objects that have been allocated but not yet freed. Interesting. Cool. I think this should be enough. We've got 17% to 10% of power remaining, even though it is being plugged in. We'll see. So yeah, leak sanitizer is the only one that's composable, and it will simply report the reported objects that have not been freed. Thread sanitizer is detecting the data races. Memory sanitizer detects undefined, uninitialized memory reads. And there's undefined behavior sanitizer, which is the most configurable one. So you can select which kinds of undefined behavior you wanna select. The reason why not all of this is enabled by default is because it would just report a ton of bugs in all the different applications. Hex type, that's from my group, detects different kind of type violations in C++ code. And Valgrind memcheck, if you don't have memory, the source code available, you can actually run this on top of binary programs as well. And you're only paying 100 to 1000x overhead. This is why we instrument the source code and not the binaries. But if you don't have the source code available, you may have to resort to Valgrind and memcheck. Key lesson here is that you should sanitize your code. You should test your code, at least with fsanitize address, because it's the simplest form of sanitization. It's very well tested. It's commonly used. I encourage you to also use undefined behavior sanitizer and other sanitizers if they apply to your code. There's the default sanitizer family. As future software developers, you should be aware of it. and then select the right one for the different projects that you're working on. So how do we speed up sanitization? Ah, we've got power. How do we speed up sanitization? We've now talked about address sanitizer in general and how sanitizer is being used as a developer tool. Now, we want to use it during fuzzing, and we want to make it as fast as possible. And we've already learned that fuzzing is only about optimizing and getting most of our cycles, as much out of our cycles as we can. So far, what I talked about are developer tools, mature developer tools that are actually being used broadly and widely in practice. I'm now shifting to a research project that we did that tries to optimize sanitization by customizing it for fuzzing and making sure that it works really, really fast for an actual fuzzer. And then at the end of the next 20 minutes or so, we'll discuss the trade-offs, why it makes sense, how much makes sense, and what could be used in practice going forward after the next, maybe in 5 years when this is actually being deployed. But you'll be able to see what the research tool is, and hopefully how it can be then used in practice and what the differences between the two are. So what's the motivation that we had? Well, we developed Fazan to target sanitization for fuzzing. And the idea here is that sanitizers are not optimized for fuzzing environments. Fuzzing environments are highly repetitive, so you've got thousands, tens of thousands of executions that hit the exact same behavior. These executions are very short, so if you have a lot of initialization overhead, this is going to be extremely costly. So ASAN in fuzzing environments is extremely expensive. So it has like 3.4x overhead on average and can have up to 6-7x of overhead, which is very, very, very high in fuzzing environments. And we try to analyze what we can do to make this better suited to the fuzzing environment. Another difference in fuzzing environments is that you always have a reproducible input. So if you trigger a crash, like you only need for ASAN, if you remember what I showed in the terminal, ASAN shows you this large list of information, where it was allocated, how it was allocated, where it was used, how many bytes off, and all this additional data. You don't necessarily need that data during fuzzing. During fuzzing, you only want to know like one bit of information. Have we violated the policy or not? If the policy has been violated, you can rerun the program with the full address sanitizer instrumentation, right? And then report and collect the full set of information, the full metadata, the full debug information, and so on. But during fuzzing, you only care about one bit of information. Have we violated the policy or not? So the question is, how can we improve this and customize this for this environment? Sanitization is costly. Well, part of this is the memory management, the 16 terabytes of memory, or allocating 16 terabytes of memory for every application that takes 0.2 milliseconds, may be a tad costly, even if it's just virtual memory. The kernel still needs to allocate all these additional data structures for the virtual memory. Right? So this is quite costly on the kernel side and incurs a lot of overhead on the kernel. In addition, the initialization of the ASAN engine is also fairly expensive. And as I just explained before, logging comes at additional cost too. So there's 365% overhead in page faults and 10x overhead in memory management time. Now, the design that we looked at after analyzing the page faults, overhead, and different kind of issues we had, we looked into designing something for this particular niche. We wanted a lightweight metadata structure that allowed us to select the right data structure for the current process. So we wanted to use locality in the fuzzing process to lower the overarching overhead of the sanitization infrastructure. The big issue that we saw is that the page table entries were very sparse and very sparsely populated, so we wanted to get rid of that. And we also wanted to minimize the memory management overhead. So our idea is that we, at runtime, select or profile every now and then to then decide what is the optimal data structure and then periodically switch between different data structure. We remove all the logging overhead because we can just reproduce and rerun a crashing input to produce the full log. And we've also optimized ASAN to get rid of some of the initialization overhead. We compile a target application 4 times. Once, and this is on the right-hand side here, once for sampling to figure out how many objects are being allocated, what the use of objects is, and so on, with a lot of metadata that tells us which data structure is best. And then we have 3 compile targets depending on these metrics. One with regular address sanitizer, one with a red-black tree, and one with a minimal data structure. And then at runtime, we switch between those different targets depending on which one is most efficient in our design. So the fuzzing module gets feedback every 10,000 executions from the through the profiler, and then learns how many memory objects are allocated, what is the distribution of memory objects, what is the size of allocated memory, and then based on this observation, it selects one of the best, or it selects the best target. Either regular ASAN, a red-black tree as a data structure, address sanitizer with a red-black tree, or address sanitizer with a compressed memory space. The underlying assumption here is that after profiling, the next 10,000 executions will be very, very similar and will trigger similar behavior. If every execution triggers a completely different allocation pattern of objects, then this would not work. So this is an inherent assumption that was luckily true, or is luckily true, for fuzzing. Now let's talk a little bit about the different targets, the new forms of metadata storage. We've got the regular address sanitizer metadata storage that allocates 16 terabytes of memory. Metadata access cost is 0.1, so this is very low, but the memory management cost is very high because you're allocating 16 terabytes of memory, right, for each tiny, short, little execution. For Fazan, a red-black tree, the memory management cost is extremely low. The metadata access cost is high. So we've got a log n access cost, right? So this incurs a certain cost. So this only works if you have very few reads and writes in the program towards the target data structures. Right? So this only works if there's very few accesses. Min shadow is like a middle ground where we try to optimize and compress the address space to keep 0.1 metadata access in a smaller address space. This is for frequent metadata access, but in a constrained address space. Let's talk a bit more about that. This was supposed to be an animation that didn't work, so you see nice figures here. Let me try to walk through it. It's similar to what you've seen before. Question? Yes. We'll get there. Good question. We'll get there in a bit. So address sanitizer, as I said or explained earlier, we've got the full address space that is being mapped, like a 4 terabyte heap plus stack plus BSS data and text and so on. This is being mapped to 16 terabyte data structure, shadow data structure in the middle. So accesses on the stack and on the heap are mapped to upper shadow, accesses to BSS and data and text section, like all the code section, is being mapped to the lower shadow memory in the data region. And the shadow memory is all of this. Okay, let me just ignore that. So the shadow memory is the shadow, bad, and shadow part. Now, if you would be trying to access and modify the shadow memory, you would want to detect illegal writes to the shadow memory as well. Therefore, you map the part of shadow memory that will map onto itself with the address translation into a bad area that is just triggering illegal accesses. This is the bad area in the middle, so you're just marking this as all bad and initializing this. Now, our min shadow memory, here we are trying to optimize towards a smaller address space. So instead of allowing a 4 terabyte heap, arbitrary stack, and arbitrary BSS data and text, so instead of mapping the full 256 terabytes of memory, we are restricting the application to 4 gigabytes of memory. And saying 4 gigabytes is all you will ever need. So we are remapping all these sections in the application to this particular area with 1 gigabyte of stack, 1 gigabyte of heap, and then BSS and data and text. So instead of 20 terabytes of total mapped memory, we only have 1.5 gigabytes. So that's 1.5 gigabytes in total, 512 megabytes for the shadow memory, and 1 gigabyte for the heap. So this reduces the amount of mapped space quite a bit. And we can actually generalize this, right? So instead of always allocating the full 16 terabytes of shadow memory, we have different designs with 512 megabytes shadow memory instead of 16 terabytes. So if you do the math, this is quite a bit smaller, and therefore needs less work in the kernel to allocate these data structures. 896, 1.4, and 2.4 gigabytes of memory, depending on if we accept a heap of 1 gigabyte, 4 gigabyte, 8, or 16 gigabyte. In practice, these two options with a 4 or 8 gigabyte heap work for pretty much all the programs out there. Because if your fuzzing process allocates more than 4 gigabytes of memory, something is really, really wrong, and you don't want to run this in a fuzzing environment, right? You want to limit your fuzzing to something that very likely allocates less than 1 gigabyte of memory. So for the majority of cases, the leftmost is sufficient, but 4 gigabytes should be sufficient in all the cases, in any case. So the dynamic switching then alternates between these different modes and avoids manual effort to select the optimal data structure, right? So you could select one of the different minimal modes, the red-black tree, or anything else. So the red-black tree has very high cost if you have more frequent accesses. But if you're just starting to fuzz, it may be efficient enough because you only have few memory accesses and very few allocations, deallocations. And this log n is not going to hit you too much. With the dynamic switching, the idea is that the metadata structure is switched according to the target's behavior, as I mentioned. And then we can increase the heap size when the target exceeds the limitation. So to answer your question, if you allocate more than 16 gigabytes of heap, you will have to switch to the regular ASAN that supports up to 4 terabytes of a heap. But this should be rare. Right. So during the sampling mode, we measure the target program's behavior every 10,000 executions. We count the metadata accesses on the stack, heap, and global, and the size of the heap to then adjust towards the correct and best policy. It's a simple counter. It's just a +1. So it's like 5 to 10% on top of ASAN. Yep, we have one for stack, one for heap, and one for global. So it's not too hard, right? So it's a couple of percent on top of ASAN. As ASAN already has like 3.4x overhead, these 3% for the counters don't really add much, right? So it's negligible compared to the other overhead. So during all the different phases, we maintain the detection capabilities that ASAN has. So we can report that this is a bug or not. And then as the fuzzer has created a deterministic input, we can just replay this input on other binaries that run full ASAN, for example. One of the optimizations that I mentioned is we avoid the initialization or logging overhead. So use a fork server at a particular placed location right after ASAN has initialized. So we can keep track. We can use shadow copies and copy on write whenever data structures are being moved. So ASAN's initialization point is moved up to right before the fork server starts. So we can actually make sure that we can recoup this cost and are only paying the initialization overhead for address sanitizer once and not every time we run the program. And then we disabled all kinds of logging in ASAN because we're only interested in crash or not crash. So the figure here shows average time of execution, and it is a bit terrible that I don't have the animation here, right? ASAN native 274 seconds, ASAN 1100 seconds. If you do everything with the RB tree, right, you don't want to use the RB tree all the time, right? So it's quite a high overhead compared to ASAN. Where if you do everything with Fazan, just 1 GB heap, we get a 43% reduction compared to ASAN. With 4 GB, we get a 40% reduction. 8 GB heaps, 38% reduction, and 16 GB heaps, still a 36% reduction. This is quite a bit, right? Now the question is which one to use all the time. So if we compare the different optimizations, if we remove logging overhead, that gives us a 20% speed up. If we move the initialization around, this gives us an 11% speed up. Together, initialization and removing logging gives us around 25% performance boost. Now compared to ASAN, if we do 1 GB or 16 GB with the optimizations, with the two optimizations, we get 43 and 48% improvement. Like the optimizations on top of the 1 gig gives us another 5% performance boost. And if we do dynamic switching, we're going to get a 48% reduction as well. So it's fairly efficient. Now you may say that always using 1 gig is better than using the dynamic structure, right? But here one of the difficulties is that you may run out of memory, and therefore you will have to switch to other options, right? Sometimes it allocates more than 1 GB of memory, and you want to make sure that in these rare cases it doesn't really happen, or you can actually run the fuzzing execution in these cases. Are we actually switching at runtime? So as it turns out, yes, we are. There's a different kind of standard benchmarks or benchmarks used in fuzzing. So we're actually switching between different kind of data structures. And for example, these two applications, RS and Vorbis, the audio codec, it actually uses the red-black tree most of the time, as is most efficient in these applications. But then other applications use the red-black tree never. And NM, here in this example, we actually see that we fall back to regular ASAN shadow memory a couple of times because we're just allocating so much memory due to some of the faults that we triggered that it just ran out of whatever our minimal data structure supported. So memory overhead, memory management time was reduced by 62%, and page faults by, 48, 50, 54%. So this is quite a lot, right? So quite a nice performance improvement, and we improved executions per second from 108 to 174. So this is quite substantial, right? So we're getting much more executions per second, much better performance compared to not using this optimization. So we are just reclaiming cycles that would have otherwise been wasted. So this allows us to vastly improve fuzzing as a process. And we discover new areas of code faster. So fuzzer plus Fazan is actually much faster than just fuzzer plus ASAN. As a quick summary on this, sanitization incurs overhead. This was a research project that studied how we can tailor sanitization to fuzzing, as in optimizing sanitization for a particular niche, where we designed a novel set of metadata structures to condense this large memory space, optimize logging, optimize initialization performance, and then dynamically switch between metadata structures. It improves throughput quite a bit by 48%, and discovers 13% more unique paths. And it gives us additional flexibility. Now, this was the research project. What would we do in practice? Would we deploy this on a real system? Which of these optimizations would we deploy? Or what would you deploy? Which of those do you think make sense? Would you remove the logging overhead? Show of hands for yes or no. Removing logging overhead, yes? So about 5, no? Also 5. So we have 80% abstentions. Interesting. Would you remove the logging overhead? Yes? Let's try this again. Still the same 5? No? Still the same 5. Huh. This is not working. So yes, you would remove the logging overhead, right? This is needless overhead because fuzzing gives you a POC, right? You can simply rerun it at any point in time. So there's no benefit of keeping the instrumentation for every single execution because you don't care, right? It's just extra overhead without any benefit. Okay.
In which cases are we talking about right now? Like in which use are we talking about?
For fuzzing, for fuzzing. Yes. So, say again.
For fuzzing, don't we use every amelioration you just did? Improvement?
This is not yet being used in practice, the Fazan, the optimization. Like we propose these optimizations. Like in regular fuzzing environments, the status quo of today is we are using fuzzing plus address sanitization. So we're paying this 3.4x overhead to run and detect these faults. The disadvantages? Well, we'll get there, right? So I'm trying to tease out and figure out how well you can assess which parts of Fazan will be useful. And how I'm asking, not everything is useful. Right? So this was an interesting research exercise to make sure what's the best that we can do. Now from an engineering trade-off, not everything is going to be deployed in practice. Some of this is going to be deployed. Removing logging during fuzzing is a no-brainer, right? You don't need this information during fuzzing because you can just rerun it with your POC later on. Okay? You agree with me on that? Yes? Good. What about forking, like the fork server to remove the initialization overhead? Would we do this in fuzzing? Yes, right? There's no loss to it. So far, so good. Would we use 4, 8, or 6 different data structures to switch between? Right. Even if your program has phases? On the usage or on the complexity of the program. Yeah, this is exactly the point I was trying to hint at. So in practice, we will likely deploy fuzzing with one of the fixed data structures, likely the 4 GB heap. It works in a majority of cases. If it doesn't work, if you allocate more than 4 GB, then something has already gone wrong, and stopping the execution there is sufficient. Right? So restricting it to 4 GB instead of 4 terabytes makes a lot of sense, and you get the majority of the improvements. You would not run a dynamic profiling in practice. This would just result in way too much additional complexity in practice. It was interesting from a research perspective to figure out, do we actually need to switch? Does it make sense to switch? And the results showed sometimes it makes sense to switch, even for a single application, because single applications have different phase behavior, right? So even in single applications, it makes sense to switch, but it's very, very rare. This also tells us that like the red-black tree only has a very, very slight, tiny performance benefit in very rare cases. So it doesn't really make sense in practice. So in the end, what you would deploy in practice on a real system would be simply the 4 or 8 gigabyte heap that gets you 98% of the performance improvements without any of the additional complexity. So you just compile your program once for fuzzing, as you do anyway, and then once for reproduction without the fuzzing instrumentation, but with the full ASAN instrumentation. Right? So this is the trade-off that we would look at in practice. Cool. Was this followable? Right? So the research project was still worth it because we tried to figure out what is the design space, right? What are all the different options? Why are we looking at these different cases? And now we learned, right? We've explored this design space, and we figured out that it makes sense to actually assign one single application in practice. You may get some tangible benefits, but at diminishing cost. The engineering cost to support 8 different versions and dynamic profiling and switching outweighs the small additional benefit that you would get. So one single configuration would be sufficient. So let me recap. Sanitizers allow early bug detections and not just on exceptions such as segmentation fault. And different sanitizers are there for different use cases. We've talked quite a bit about address sanitizer and the policy, which enforces probabilistic memory safety by recording all this metadata. We've talked about memory sanitizer, that targets uninitialized reads, thread sanitizer, undefined behavior sanitizer, hex type for type confusions. And we then studied on a research project, on a recent research project, how much it makes sense to tailor sanitization towards a given environment. And if you're running billions of CPU core hours, it may make sense to customize your sanitizer for this environment if you get a 2x performance improvement. Right? So the slight engineering cost of adjusting your address space for a 2x improvement is very likely worth it. So as a summary, you should sanitize all the things, learn how to use the right sanitizer in your code, and then abstract that and use it in practice. This is all that I had for today. If you have more questions, let me know. Don't forget to submit the official evaluation, which is also due. Please provide some additional detail. We'll do one more evaluation towards the end, where you will give me feedback on Moodle on how to adjust. This will come up. But please fill out the official one as well, because this is how I will be evaluated, and I will be happy if you do so. Cool. Thank you, folks. If there's more questions, let me know. Otherwise, I'll see you next week. Cool. Thank you.